A modern wind turbine is a massive, dynamic machine, constantly adjusting its pitch and yaw to extract power from chaotic weather patterns. The same continuous adjustment is required for smart grids, distributing that power across entire continents. Keeping these immense networks stable requires absolute precision. We cannot rely on trial and error to figure out how they behave. The control of these physical systems requires a sequenced, rigorous mathematical methodology. If you want to know how a 300-foot turbine blade reacts to a sudden gust, you do not test that by arbitrarily tweaking parameters on the physical tower. Empirical testing on high-stakes machinery is exceptionally dangerous. It risks catastrophic mechanical failure and costs millions of dollars. To avoid physical disaster, engineers extract the physical properties of the real-world machine and reconstruct them inside a controlled mathematical simulation. We test the math before we ever touch the hardware. This chart outlines the universal design methodology. First, establish control goals and identify specific variables. Next, we write exact specifications, defining allowable error margins and response times for safe operation. Then, we obtain a mathematical model, abstracting the physical actuator, sensor, and plant into equations. Because every subsequent step in this workflow builds on those equations, the accuracy of the mathematical model determines whether the final physical system functions as intended or tears itself apart. To build that accurate model, we have to isolate the specific mechanical properties of the system. Let's look at translational mechanics, systems that move in a straight line. A translational linear mass moved by a forward force generates opposing friction and acceleration forces. Adding a translational spring creates resisting force proportional to displacement. A damper provides resistance scaling with velocity. Mapping these vectors translates the mechanical setup into one time-domain differential equation. By rigorously applying these Newtonian principles, we capture the physical behaviors of a machine and bind them into strict, predictable mathematical laws. There is an immediate problem with this model. Solving complex differential equations in the time domain is incredibly tedious and computationally inefficient, making it nearly impossible to design a dynamic controller. To bypass this computational bottleneck, engineers use a mathematical tool known as the Laplace transform. The Laplace operator transforms the heavy calculus of the time domain into the complex frequency domain, the S-plane. Here, those differential equations become straightforward algebra. This resulting algebraic fraction is the system's transfer function, dictating exactly how the output responds to a given input. This transfer function acts as the fundamental genetic code of the machine. Simplifying the math into this manageable form makes the actual design of the controller possible. Right now, our transfer function only represents the raw, uncontrolled machine, what we call the plant. If a wind gust pushes it off course, the plant has no way to detect or correct its own error. To fix this, we build a closed-loop block diagram architecture. We place our plant's transfer function in the center block. Next, we read the plant's output with a sensor, feeding that signal back. That feedback meets the target input at a summing junction, outputting an error signal. Finally, we insert a controller block into the error signal's path, continuously manipulating the input to drive the error to zero. Closing this loop transforms a static mathematical model into a dynamic, automated system capable of reacting to its environment. With the loop closed, we return to the final step of our master design methodology, optimizing the parameters and analyzing the performance. We iteratively adjust the controller's internal values. The goal is to ensure the math remains unconditionally stable and that the physical machine will hit the specifications we wrote down at the start. Looking at this time response plot, we see how tweaking a single parameter changes the system's behavior. When parameter Ka is 60, the response exhibits heavy oscillation, overshooting the target. By tuning it down to 30, the system smooths out and stabilizes. By forcing the chaos of the physical world through this rigorous mathematical workflow, engineers verify a machine's stability in simulation, allowing them to deploy massive, automated systems into the real world with absolute confidence.